Hello, hello, welcome back. This is Unit 7, Day 5, Part 2. This is the second video on washers, okay? The previous video was video 1 for discs, but I broke this up into 2 separate videos, and we did discs already, and we are now onto washers, okay? So Part 2 actually has 2 videos to it. Video 1 is discs, and video 2 is washers, and this is what we're doing today. All right. This is the last lesson. Kind of sad. It's bittersweet. All right. We left off with video 1 of Unit 7, Day 5, Part 2, with this problem. Okay, it's already done. I'm not going to go over the entirety of it, but it was the natural draft cooling tower. Okay, and that was the last disc problem that we're going to do. We are now going to move on to what we like to call washers. Now, the region bounded by y equals x squared, okay? The region bounded by y equals x squared and y equals 2x is revolved about the y-axis. Find the volume, okay? We are going to use a horizontal slice, and I'd like to pull this picture up here. Let's do this. Might be easier on the eyes, okay? So let's go crazy here. Let's go orange. Didn't use that at all last video. So y equals x squared is this line right here. Boop. And we'll go purple. Okay, that is y equals 2x. That's this line here. Now notice, I only care about the solid in between those 2 lines. Yellow. I only care about this. Okay, before, all of our shape was, it was just one graph rotated, so there wasn't really a whole. So I care about that. And when I revolve it, it's going to revolve to this part right here. Okay, I think you kind of get the gist. Okay, so there's going to be this hole in the middle. Think of this as a cup. Okay, let me do this. Let's go gray. I love gray. Okay, here's the top of my cup. Okay, and it comes down like this. Comes down like this. But then it's hollow because you need to put liquid in it, right? Most glasses or cups that you drink out of need some sort of cavity or opening here. And we've got this cup here, okay? So it's going to look like that on the outside. Let me just straighten this up. Okay, but on the inside, what we don't see is this thing right here where it's, it's how, and all this is where my water goes right here. This is all empty. This is empty space. All right, and what we have here is this disc that represents where the actual material filling is going to be in our glass. Okay, this is known as a washer. Let me get rid of that. Boom. This is known as a washer. In case you didn't know, most guys know, and I shouldn't be sexist like that. A lot of girls should know as well, and a lot of guys should know. Maybe some girls don't know, and maybe some guys don't know. When you're building something with nuts and bolts, often, if I'm putting something into a piece of wood right here, okay, and I'm putting a bolt or a wood screw or anything through. A lot of times they put this thing down here that's called a nut that screws onto it so it doesn't pull back up. But instead of having my wood sit right flush against the screw head there, what they do is they put a washer there, and that's why it's called a washer. It's a circle like this, and there's a hole in the middle of it, and the washer's like that. So the bottom of the screw doesn't touch the wood. This nice flat washer does. Okay, and a washer, it's just that. It's solid with a hole in the middle of it. Now, let's use some common sense here with the way we're going to figure this out. That's your nice daily life lesson from old Mr. Visca there. Your Uncle Frank. All right? But this disc now has a hole in it, making it a washer. So draw the solid, which we did in gray, and draw the slice, which we can again to set up the volume of the integral. Now let's take a moment to realize that we really know how to do this already. Okay? And we're going to take two pieces of background knowledge that we recently learned about to figure this out. And yes, we will integrate it and find the volume. All right? So first of all, since Unit 7, Day 5, Part 1, not the last video, but the video before that, we said volume is really, I'm going to use pi if it's circular, and a washer is circular. There's two circles there. There's one circle on the outside and one circle on the inside. Okay. The volume is pi times my integration from two limits of really the area. Okay, really the area. All right. Now, and then I have some dx, whatever. Yes, I know it's my radius squared for a circle, but it's the area. Okay, so now let's look at this washer that I crudely drew here. If I want to find out the area of just the washer, not the empty hole, I mean, let's go back to geometry, probably even earlier than that. I'm going to take the area of the bigger circle, and I'm going to subtract the area of the smaller circle, okay? So I take the area of this completely, and I subtract the area of this one. This minus the area of this one will ultimately give you, oh boy, wait for it. No, not that. Come on, highlight, Frank. Now's your moment, Frank. Don't blow it. It's going to give you, look how deep purple that looks over the blue. That is so cool. Okay, it's going to give me this. Okay, this area minus this area, okay, is going to give me this area. So I find the area of the bigger circle, and I subtract the area of the smaller circle, and that gives me my washer. Now, we know how to integrate the area of a circle, and we know that gives us volume, which is what we're looking for. Find the volume. So let's take a look at something else we already know. It is revolved about the y-axis. That means my bounds should be y's. Upper bound is 4, lower bound is 1. So let's integrate this from 4 to 1 pi. Okay. Now let's figure out what the area, okay, let's figure out the area of the bigger circle is going to be. Well, the radius will be from this point, boom, to there. So it's the outer equation, x squared. Well, if my bounds are y's, I need a dy here, and my equation that I integrate should be y's. I shouldn't put x squared in there. Okay, I need, in terms of y, I need my y variables here. So I need to solve this for x in terms of y. 1x, okay, so the square root of y equals my 1x. Okay, so this is what I'm putting in for my radius. Let's not forget, for a circle, my radius squared. That's the area of the bigger circle. Okay, so let's call this bigger radius capital R. Okay, that's this right here. This equals capital R for my big radius. I got to square that big radius. But then I want to subtract, let's do this, we'll do this in gray. I want to subtract the area of my smaller circle. It's the same thing I have here. It's still from 1 to 4, my y's, it's still dy, but my smaller radius goes from here, the center, only to here, which is this equation, okay? That purple line, and the purple line is this here. Now again, I want that. That's my little r. We'll call the gray one little r. The big radius is capital R. And that small radius is my lowercase r. So I still need y equals 2x. I still need that means x equals. I need my y variables here. I need it in terms of y. So the only thing I got to do, okay, thank you for reminding me, I should put that down. The only thing I really need to do to get this in terms of y is I'm going to divide by 2. Y over 2 equals x. This is what my smaller radius is, okay, in terms of y. Of course, I need to square my radius, right? Because area of a circle is pi r squared. So instead of area, we're going to do r squared because that's the area of a circle. Now, I could do it like this. Okay, I could do 2 separate integrations, but let's just do 1 integration, okay? If I factor out, and this is where the magic happens, kids, if I factor out my pi, and I multiply that by the integration from 1 to 4 of this, minus this, I get the same thing, right? Because when I integrate, I still just go down the line. I integrate this first. Oh, that's supposed to be 4 to 1. Actually, that's supposed to be 4 to 0. Where'd that 1 come from? Oh, my goodness. Oh, my goodness. Do you know where that 1 came from? I was still thinking about this one, 1 to 4. Sure, Visca, I was. I was thinking 1 to 4. Okay, from 4 to 0. I am still going to integrate this from 4 to 0 and this from 4 to 0, right? It's the same thing. So when we do a washer, we can do them separately and subtract them, but this is the real format of how we do a washer, okay? And you'll see it on the next slide. I take the bigger r squared minus the smaller radius squared. I integrate that and multiply it times pi. That is the money shot. That's what we're doing, okay? That's the money shot, and that's what we're doing. All right, so, I mean, if I wanted to, and I can, we could do this algebraically. You know, we only got 2 problems to do, so we should do it algebraically. And then try it on the calculator to make sure we're right. Why not? Why not, kids? All right, let's do this. I'm excited. I'm excited to do math, in case you didn't know. Okay, so the first thing I'm going to do is I'm going to simplify this first before I even integrate it, and simplify this. It's going to make life easier. So I've got pi of the integration 0 to 4, not 1. When I simplify this expression, it's just going to be y minus. When I square both of these, I get y squared over 4 dy. Well, let's just integrate these. Okay. So the first one is y squared over 2 minus y cubed over, now I put 3 in the bottom with my 4, so that's going to end up being 12. And I want that from 4 to 0, and oh, by the way, I'm multiplying it times pi. All right? Okay, let's do our work here. Pi times, let me put a 4. It's 4 squared over 2 minus 4 cubed over 12. All right? We'll do this in a different color. Here's putting in the 4s minus putting in the 0s. And you know how much I love putting 0s in, because now I got 0 squared over 2 minus 0 cubed over 4. That just turns into a big old 0. So let's simplify. We have 16 over 2 minus, what is that, 64 over 12. Still got to multiply times pi, which means we have pi times 8 minus, no, 4 has to go into both of those. 4 goes into this bottom one 3 times. And 4 goes in the bottom, the top one 16 times. Yeah, 16 times 24. Yep. Now let's combine them. 8 is like saying 24 over 3. Okay, so 24 minus 16 is 8 thirds pi. This is an exact answer right there. Let's see if we did our math right, children. I'm going to put in the calculator. I'm going to put this purple integration in the calculator. And first, let's see what 8 thirds pi is. Okay, and see if that's going to be a correct answer for us. Now, let's turn this on. Clear. Let's do alpha y equals enter 8 over 3 times pi. This is what we got, 8.378. Okay, that second 7 will round up. Let's see, it's exciting, kids. I put my pi, I go to math, 9, from 0, not from 1, but from 0 to 4. And just to let you know, you see how there's parentheses by default? So this is what's going to be going in just as it is. So even though I have the default parenthesis, I'm going to start by adding another parenthesis there. I had kids in class be like, why are you double parenthesizing? Because I cannot put a square out here. So everything that I do is going to be squared inside, if that makes sense. So, parentheses, the square root of 4. Yeah, why am I so obsessed with the bounds? 1 and 4 and 0 and 4. The square root of x squared. That's my big radius. My big radius squared. Minus my smaller radius, which was alpha y equals enter x over 2 squared. Here is my smaller radius squared dx. Now, why did I put, okay, why didn't I just put x in the first parenthesis for my r? And how come I didn't put x squared over 4? I like to put the problem before I did any simplifying into the calculator, before any simplifying, because a lot of the times the kids will do something very quickly because they know it good, but because they do it quickly, they make a mistake. And sometimes that happens to me. So in order to ensure I didn't make a mistake with my simplifying, the easy simplifying in the beginning, I'm going to put it in just like I got it before I did any work to it. And there we go. Perfect match. 8.378. Bam. So that is approximately 8.378. Good. Good and good. Okay. So, in a nutshell, whenever I use this application of method of slicing is called washer method. Okay, this application of method of slicing is called the washer method. The shape of the slice is a circle with a hole in it. So we subtract the area of the inner circle, duh, from the area of the outer circle. And how do we find the areas of these inner and outer circles? Pi r squared is the outer circle or the bigger circle. Pi little r squared is the inner circle, and I just subtract them. Okay, and there you go. That is your go-to. Anytime you're using a washer, all right? Anytime you're using a washer, you just write it like this. The equation that's the bigger one goes there that you square, and the equation that's the inner one or the smaller one goes there that you would square. All right? Let's try another one that is not necessarily revolved around the x-axis or the y-axis. I know we talked about this a little bit, but we haven't done one. I mean, I think we mentioned it in the last video. This one right here, this is a good one. This is actually the same exact shape. See, it's the same two problems. It's just like shifted and flipped. So we should technically get the same area, 8 thirds pi, okay, which is 8.378. So I'm going to write this right here, 8 thirds pi, which is approximately 8.378. Remember, that was like a 7 and a 5, but we rounded the 7 up. So this, in the back of my mind, I'm knowing this should be the answer. Okay? So we're still going to use the same volume. This is a washer. Okay? This is a washer. I still need to take, all right? I still need to take my bigger radius and square it minus my smaller radius squared. Okay? Pi is on the outside, my bounds, my dx or dy, whatever I'm using. Just because it says dx here doesn't mean I'm using an x. That's just a general formula. Okay? So let's look at our washer. That's the first thing I'm going to do. Let's go purple. This is my washer. Like here and here. Okay? Now, if I were, now that's not, it's not around the x or y axis. I can't say, oh, it's revolving around the y-axis, so I'm going to use y's and dy's or whatever. But when, you know, they say look at it as horizontal, because horizontal will be revolved around the y. This is what I do. If I were to shift this toward one of, oh, great, it's not, I knew that was going to, let's do this. Come on, let's group it so it moves together. Group, yeah, you. Okay, if I were to move this to the x-axis, that's obviously not rotated around the x-axis. If I move this to the left, that is clearly rotated around the y-axis. Okay, so if I were to rotate something this way, if I draw the arrow right on top of it, okay, that would be a rotation around the y-axis. That's how I remember it. Okay, another thing is, well, if I'm rotating it around here, the y-axis goes up and down, doesn't it? It's the y-axis that goes up and down. Or if you're one of these technical people and you want to say, well, it's horizontal, so I know it goes around the y. There are multiple ways for you to remember that and to make that connection. Me, I just look at this and say, if I had to put an axis through the middle, the y would go through the middle, not the x. So it would rotate around the y if it were on an axis. Okay? It is not, but if it were, it would. That means I need y bounds. Okay? My y bounds are from 0, that's the bottom, to 4. It's not 1, it's 0 to 4. Okay? And I'm going to be using dy. So let me start to set this up. It's the integration from 0 to 4. Pi is on the outside. Now I need my bigger r squared minus my smaller r squared dy. Okay, minus. So I just got to figure out what the bigger radius is and the smaller radius is. Okay, obviously, if I go from the middle here, I'm going to try to avoid using yellow. Someone at home, when I was teaching a class over Zoom, said they really couldn't see the yellow writing too good. So I don't know, probably an Apple person. I'm an Android person, so I'm just teasing. This is not the bigger radius. Obviously, the bigger radius goes to the outside. So the bigger radius is going to be to here. But first of all, I need that in terms of y. We already did that. Last time, in the last problem, we started with this and just said x equals y over 2. So this is the same thing as saying x equals y over 2. Remember, we need it in terms of y to plug in here. But I can't just say it's y over 2 because what? Because it's not on the y-axis. Okay? See this here, y equals 2, that's where it's rotated around. Okay? So if I want to know this distance from here to this point here, okay, if I want to know this distance, I take the number 2, which is right here, and I subtract. Okay, let me show this to you. From this point to this point is 2. It's x equals 2, rather. Okay? And I subtract this thing. Okay? I subtract this distance right here from this point to this point. You know what that is? That's right on my graph of y equals 2. Okay? So if I want, oh, you stinky you. If I want, and I'm going to do this in yellow, I don't care what they say, from here to here, I take my red line, which is x equals 2. Yep, that was weird. Let's unmove that. I take this line, which is x equals 2, so I get a value of 2, and I subtract this line, which is this value, x equals y over 2, and it gives me this yellow one, okay? So I'm really going to take my out 2, okay, x equals 2 is what it's revolving around. I subtract my other x, okay, which happens to be y over 2. So I take 2 minus y over 2. And that's my biggest or outer radius. Okay, I got to subtract my two x values. Let me explain this, because I can imagine someone staring at the screen like, what? Someone's like, Visca, don't, I get it. But there are some people that are like, what? I take this point, which is x equals 2, and I take this value. That happens to be y divided by 2. Okay, whatever x value is here, okay, it's whatever my y value is divided by 2, because that's where x equals y divided by 2. Okay, that gives me the point, this distance of my radius right there. Okay, how come? Because once again, it takes this whole thing, which is 2, and it subtracts this part of it, which is whatever y is divided by 2. Okay? And that gives me, my friends, this one right here. 2 minus y over 2. Now, the inner one is the same way. The inner one is the same way. All right? I want the smaller radius. I go from here to here. I'm still going to take 2 and subtract whatever value is here. It's not at 1. Whatever value is here. Well, that's on this graph this time. Okay, it's not on the outer graph, it's on the inner graph, which is x squared. Again, I got to set that x equals. I've got to get my variable to be the y, so I say x equals the square root of y. So this value right here is whatever the square root of y is at this point. Okay, square root of y. So I take 2, I subtract this point from here to here, which is y over 2, and that leaves me this part, which is the radius, okay? So it's 2, which is the x where I'm rotating it, minus my small r, which, oh, by the way, square root of y. X equals square root of y. There you go. Now we just plug it in a calculator. Okay, let's put it in there just as it is. Okay, the calculator is going to give you 2 parentheses here. So I take my bigger radius, which is 2 minus y over 2, and I square it. Minus my smaller radius, which is 2 minus the square root of y squared. I'm going to put that right in the calculator. Oh, come on. Now this don't break apart. Come on. Come on. You stink. All right. So anyways, I'm going to put this in the calculator just like this. This, I don't need the r's anymore. Okay, and you know, in the calculator, we don't have y's used as variables, so I'm just going to put x's where those y's are. And let's see if we can come up with that 8 over 3 pi, or that 8.378. This is going to be good. It's going to be good. Let's get rid of this here. We'll turn this on here now, boy. And that's what we should come up with. That was a previous problem. It's the same shape, same washer, same 2 equations, same volume. So we should end up with the same thing. Second pi, math 9 from 0 to 4 still, please, Lord. Parenthesis, 2 minus alpha y equals center x over 2 instead of y over 2, parenthesis squared. That is my first, that is my big radius, okay? That is my big radius squared. Minus, parenthesis, 2 minus the square root of x pop out, parenthesis, square it. That is my smaller minus my smaller radius squared dx. Bang, 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 bang. Hey, wow, that took a while. For a second, I thought I was going to come back with an error. I'm like, don't do it. Don't you do it. And it didn't do it. We got the same exact number. Well, tens, hundreds, thousands, 10,000s, hundred. I mean, that's exact to the 100,000ths. Okay, and then remember, sometimes the integration is done slightly different on the calculator than it is on paper and pencil. So, I mean, that might be off, but we're looking at here. We're good to go, and we're fantastic. Round that 3 places, it would still be 8.378. And we're done. We are done because after this is shells, and we are not doing shells because I really haven't seen them on the AP Calculus AB exam, and that's what I prepare my class for. Okay, let me take this moment. Oh man, 30 minutes, 2 problems, a lot of explaining. Look, let me take this moment to say I have enjoyed this journey with you. It has been great. It has been wonderful. And as I teach the same courses and I change things up a little bit, I redo videos over and over again. But the last video for the last lesson for the class is always a special one. And that means kids that I've taught for 3 years, because I teach Algebra 2, then I teach them in pre-calculus, and then I teach them in calculus. They are graduating and they're gone, and I've made connections and relationships with these kids for 3 years, and they're awesome. And you know what? You're awesome too for having listened to this and having listened to me banter and listen to me go on and ramble. Some of the jokes were spot on and great. Some were corny. I get it. You know, I am a dad, so dad jokes fly out abundantly. But you know what? All I want for you in life is to be happy, because when you're happy, other things that aren't as important, you know, don't take up a majority of your life with stress and anxiety when you're happy. Just be happy, be good, decent people, be nice to other people, and be yourself, more importantly. And if no one likes you as yourself, you don't have to be their friend. You make friends with people who like you for you. That's it. Bottom line. All right? Have a great rest of your year. Do fantastic on the AP Calculus AB exam. You got this. And, hey, drop a comment. You know, ring that bell, ding, ding. Follow me, do whatever you want to do. Not literally. If I'm walking out of the school building, don't be like, "But there's Visca." They start looking at some weird kids are following me. Don't do that. But you know what I mean. All right. See you later.